This goes down to 50. This goes up to 5,700, and this goes up to 50, because 50 and 50 gives me the original 100. And then I can put a 2 here for 2 half-lives. This would go down to 25, this would go up to 75, and this would go to 11,400 years. I usually don't ask questions for more than 3 or 4 half-lives, so I'll break this apart to 12.5 over here. This becomes 87.5, and this becomes another 5,700, becomes 17,100. Now there's nothing you can do to change the half-life of these. So if you crush the rock, you heat it, do anything to it, it will have no effect. Can it change the half-life? Absolutely no. Not going to happen. All right, rock layers. If rock layers are undisturbed, then we use what's called the law of superposition, the oldest layers on the bottom. Now occasionally what happens is we get an unconformity where the layers have piled up on top of each other, and we have a gap in the fossil record, because in an unconformity we have uplift for an area, then we have weathering and erosion, and then we have subsidence, and then we have new deposition happening, and that leaves a gap in the rock record. Now we also have these rules that if we have intrusions or faults, they have to be younger than the rocks that they are in. And marine fossils on top of a mountaintop indicated that the land's been uplifted, because marine fossils were formed in the ocean, and we find a lot of places where marine fossils are found high up. It tells us that we've had some uplifting, and uplifting, folding, faulting, they're all evidence of what we call crustal activity. Sometimes we can use contact metamorphism to figure out which came first. So if a rock layer has these whiskers, or they call them ticks in here, the rock layer had to be there before, it had to be older. So this rock layer was here before this igneous intrusion, but this rock layer up here, it doesn't look like it was. And I could tell that if it was, and this was an intrusion that burnt its way through here, I'd see those marks on the top too. Okay. All right, be able to tell the difference between folding, faulting, and tilting. So a fault, let's see what we got here. A fault is when one side goes up, the other one goes down. Here's an igneous intrusion. Folding's like this. And rocks are originally deposited horizontally, so tilting is a sign that crustal motion has happened. Volcanic ash makes a great time marker. So I'm going to use that little bit of space here to talk about volcanoes and stuff. So when we have a volcano that's erupting like crazy, it's going to send a lot of ash into the air, and that ash is going to be deposited in a wide area, large area, over a short period of time. So let's say thousands of years go by, the volcano dies out, and we get new layers of rock piled on top of it. Okay? Every time there's a volcanic ash eruption, these things have their own chemistry. It's kind of like on the forensic files where they find like chip paint on a car that's been crashed into, and they analyze the paint, and it's just got a certain chemical makeup that makes it only found on Ford cars or something, and they figure out it had to come from this guy's car, and they arrest him, right? So each one of these layers here has its own chemical signature. So if I find this anywhere in the earth, around the earth, because it's been shot all over the earth, I know it's the same age as the other layers that correspond with it. Okay, index fossils make good time markers because, first of all, they're widespread. Just like the volcanic ash, they're widespread. They have a large geographic range. The other thing is they have to be short-lived. That, unfortunately for them, their existence on Earth didn't last very long before they became extinct. And they really should be easily found. They should be the type of fossils that aren't really hard to find, so they should be fairly common. So we have a list of all the index fossils on the reference table here, and you can match them up. I'm sure when you get into the Barron's book, you're going to be doing some things with these guys over here and how they match up here with the different times. Okay? Geological history. How did the atmosphere first form? We go back to the molten earth and lots of volcanoes spewing gases all over the place as the earth cooled and creating an atmosphere. And this atmosphere had no oxygen in it. It was poisonous, actually. So the volcanoes just spewing out steam, creating the early atmosphere. How do we get the oxygen? Well, once the oceans formed, early algae took CO2 and changed it into an atmosphere with the carbon taken out, changed that into oxygen. So it was early algae. And if you need information about when that was and what happened about that early algae, you can find that information over here, where we got that oxygen into our atmosphere. Okay? Now, Precambrian time, this is 4 billion years long. What type of life existed? Only the simplest forms, and that means that we rarely find fossils, that fossils are really rare. That's because they were soft-bodied organisms, rarely found any fossils from that period. Now, in the time scale, when we look at the time scale on here, it doesn't look like Precambrian is really a long time, but when we did that lab with the tape, if this was the tape for the Earth's history, Precambrian was like this much of that tape. So this was Precambrian. And then the other errors we broke down in there. So Precambrian is a major time. Now, life evolved from very simple organisms, and over time they became more complex. And we really call that idea evolution, that things form from simpler to more complex. Now, we think asteroids had an impact on our planet. Asteroid impacts are thought to be the cause of mass extinctions. We talked about how the dinosaurs died about 65 million years ago because of an asteroid impact. And asteroids do leave craters behind on the Earth, but unlike the Moon, the Earth has weathering and erosion going on, so while a lot of those craters disappear, on the Moon those craters remain, and we can still see them today. So let me just remind you about that asteroid impact information. It didn't just wipe out the dinosaurs. You can see they mentioned the ammonoids, and if you look over here on these timeline here, you can see the dinosaur line stops here, and also the ammonoids. Ammonoids were animals that kind of look like these snail shells down here. Okay? All right. Weather variables, air pressure. The instrument we use is the barometer. Oh boy. B-A-R. Okay, barometer. And we use millibars or we use inches of mercury, Hg for mercury. Okay? Temperature, thermometer is the device. And we have different scales. We have Fahrenheit, we have Celsius, and we have Kelvin. And all the conversions for the barometer and so on. They're on your reference table. You probably remember where they are. Okay? There we go, if we have to convert things around. Okay, dew point, relative humidity. Dew point is the temperature at which precipitation is going to occur. Temp at which precipitation. So on your station model, sometimes you'll see something like this on your station model. Here, just draw this out with a couple bands on here. You see an air temperature, maybe it's 32 over here, and then it's 31 over here. This would be an indication that we're really close to the dew point temperature and rain is likely. Relative humidity is the amount of moisture in the air, and what I'll just put down for relative humidity is 100% usually equals precipitation. So the closer we are to 100%, the more likely it is to rain. Now, for the dew point and relative humidity, we're going to use a device that's called a sling psychrometer. And that's going to give us a wet bulb reading and a dry bulb reading, and the rest is up to you. We've done this chart a lot, and I think that you should be pretty good at using that. Wind direction. Winds are always named from where they came. So named for where they came, not the direction that they're blowing in. It's named for where they came. Okay? Wind speed is typically measured in knots, and what we're going to use for this is an ammeter. Oh my gosh, that's the wrong name. Let me go back up to wind direction. We use a weather vane for that, and this is called an anemometer. An ammeter is something you use to measure current. Okay. Okay, pressure. The reason we have pressure is unequal heating. High pressure. High pressure is usually cold temperature or cool temperature. Low pressure is usually warm. High is usually clear. Low is usually cloudy. Precipitation. High is usually dry and low is usually humid. Okay? So the direction of the air around the pressure systems is different. Around a high, it's outward and clockwise. And a low is inward and counterclockwise. And wind always goes from the high to the low. Okay, let's move to the next page. Winds are caused by the uneven heating of the earth and the differences in density. And basically winds are part of convection cells. So when we have an area that one part gets hot and the other part remains cool or cold, hot air rises. It does RECC, rises, expands, cools, and condenses. I'm going to bring this over here. Cool air comes down, and we get our convection cell like that. The wind blows from the high to the low. What do I mean by that? This is low pressure over here because it's lifting. Over here is high. And because it's lifting and doing this, we're going to get our rain, our low and lousy, and over here, high and dry. All right, so if we go back over here about this, winds blow from the high to the low. Isobars close together will give us high wind speed. Okay. Then we have this phenomenon around beaches where during the daytime when the sun is out, okay, the land, which has a high specific heat, heats up faster and becomes warm during the daytime. And so the air over the land moves up and over the ocean moves down. And during the day we get a sea breeze, okay, because this is going to be hot. And this is going to be cool over here. This has got high specific heat, low specific heat. And this has high specific heat. But then at nighttime, when it's nighttime, the water, which is a poor absorber, is also a poor radiator. The water is now warm. It's heated up all day. The land is now cool, and we get the opposite.
Hello, everyone. Our evening will be wrapping up in about 10 minutes, so it's time to announce our raffle winner.
All right, I'm going to keep on going while these people are talking behind me. All right, dew point temperature. We already talked about the air temperature at which the air is saturated. Here is your dry bulb, wet bulb. When the air temperature equals the dew point temperature, you have 100% relative humidity and 100% chance of precipitation.
738.
Relative humidity is the percent. Condensation forms clouds.
Again, the
steps for
winning raffle ticket
condensation
number is 743738.
The air rises, it expands, and it cools to dew point,
We have a
and
winner.
we get condensation.
Congratulations, and again,
The
thank you
Coriolis
so
effect
much
is
for
the
another successful
deflection of the
expand
Earth's,
year. Good night.
the deflection of things like wind and ocean currents due to the rotation of the Earth. And northern hemisphere things deflect to the right. Air masses refer to a bubble of air which has a certain humidity and temperature over the surface that it forms. And MT would be what we call a maritime tropic air mass. And because it's maritime tropic, maritime means it's formed over the ocean, it's going to be humid, and it's forming from the equator, the tropics, so it's going to be warm. Continental polar. As an example, continental would be dry and polar would be cold or cool. Okay? So I'm sure in your Barron's book we're going to look at some different types of air masses there, and you'll get your information about that. A front is a boundary between the two, and what you have to remember is in a cold front, cold air forms a wedge here and creates really severe weather, like thunderstorms and possibly tornadoes. In a warm front, the warm air moves upward and the cloud is expanded, and so we get steady rain. In an occluded front, the warm air is popped up above here, and once again we get rain. Then we also have a stationary front. Now, all the weather in the U.S. moves to the northeast, and so in a map of the United States, where here's Florida, here's Gulf of Mexico, and so on, almost all the storms move in this direction. Now, that's not always true with every place, and so for different latitudes, you might find the storms moving in different ways, and the way that you can tell the direction that the storms are moving is by looking at this. See, we're in between 30 and 60, and it shows we have southwest winds, which moves our storms this way. And one of the things that move the storm are these high-level air currents called jet streams. So you might hear that referred to what moves the storms along, are these jet stream air belts. All weather moves to the northeast. Station models, we learned about conversion. Remember the 500 rule? That on a station model you can only write down 3 numbers. And so if this is my station model over here, and I'm just put this wind thing out like this, and I see the number, let's say 982, I have to do the 500 rule. And the 500 rule says that if the number is less than 500, hold on a second. I need 10 more minutes. Bye-bye. If the number is less, you put a 9 on it, and if it's greater, you put a 10 on it. So if I go the other way, if I want to convert this and put this on here, this would be 009. This one over here, if I wanted to put this on here, this is going to be 9600, and this one over here, this would be 10.0, and I'll put millibars for each one of these, like that. Okay? All right. Hurricanes, preparation for hurricanes, you pretty much put everything you did with the earthquakes on that. Tornadoes, same thing as the earthquakes. You just use your common sense on that. All right, so we are up to stars right now. Stars are going to give off electromagnetic radiation. The sun radiates solar energy, and the type of energy that it mostly radiates is visible light. So when the visible light comes into the earth, it's what we call short wave, and the earth absorbs it but re-radiates it at a longer wavelength. So it comes in as visible, but it leaves as infrared. And what we learned is that the greenhouse gases are trapping that in. What are those? CO2, water vapor, so put vapor, and also methane. Those are some sources that trap in. Notice ozone is not in there. Ozone's only blocking out ultraviolet radiation. Okay, the Earth radiates heat energy as infrared heat energy. Good absorbers of light. If you're a good absorber of light, you're probably going to be smooth, and you're going to be, oh, did I say smooth? I'm sorry, that's totally wrong. Your good absorbers of light are going to be rough, and they're going to be dark. And good reflectors are going to be smooth, and they're going to be light. Good absorbers of light are also good radiators. Like I said, a good absorber is a good radiator. Specific heat is the resistance to heating, and you can get your information on specific heat on the front page of the reference table right over there, right? Okay, good absorbers, and then we have high specific heat. Which takes longer to heat up, water or granite? The answer is water. It has a higher specific heat. Now, I didn't really talk about these things in class. I didn't really get into them, but they could be on the regions. Conduction is the transfer of energy in solids. And I use the idea of a frying pan. If you have a frying pan, let's say this is the handle of the pan, and this is where you're going to put your food, bacon or whatever that you're cooking. You're going to put it over a fire here. What's going to happen is the molecules in here are going to vibrate because of that. This is going to heat up first, but that heat is going to be transferred by molecules to molecules. So conduction is the movement of energy through a solid. Convection, we've already talked about. That's where one side goes up and the other side goes down because of density differences. And radiation is the transfer of energy through a vacuum, like how the sun's energy gets to the earth. All right, here's the type of greenhouse gases: CO2, H2O vapor, and methane. All right, let's keep going. Greenhouse gases act to trap in the infrared. Okay, we talked about the water cycle. Infiltration is when water sinks in. Infiltration occurs when the land is. Okay, so a couple things on here. We want it to be permeable. We want the land to have a flat slope to it. We want the land to have a high porosity to it, a lot of pore space. And the land has to be unsaturated. It's best if it is dried out. Runoff occurs when the land is unpermeable, is steep sloped, has a low porosity, and is saturated. What increases stream discharge? What increases it? More stuff in the streams? Well, this is weird. Infiltration could. I guess if you had more water going into the ground, you might fill up the ground with water, but it's really more rain, more runoff, more melt will give you more discharge. Now, porosity is the percent of pore space, and a lot of times they'll give you diagrams like this. Each one of these has the same amount of pore space. This just has big pores, but few of them. This has small pores, but many. Okay? Grain size increases permeability. So as the size of this becomes larger, the water goes faster through it. So the larger the size, larger, usually faster. Now I do want to point out that if I mix these up, the small beads will fill in the holes here, and I'll have less porosity, less permeability. There's also something called capillarity, the upward motion. And actually this one will have the greatest capillarity. That's the capillary winner. All the same porosity, best permeability here, but this one pulls up the water the best. It also retains water better. As grain size increases, capillarity decreases. You can see that. All right, climate, long-term weather for location. As latitude increases, temperature decreases. As elevation increases, temperature decreases. And then we have the idea that if you're located near the coast, your climate is going to be different. You're going to have milder summers and warmer winters. We can also tell if a location is in the northern hemisphere because the summer temperature will be during July and June. And so we see these are northern. And this one over here, this one must be inland because it has a great range. This one's probably near the coast. We also learned about how mountains affect the weather. And so here's the windward side. We get what's called the orographic effect. This rises, expands, cools, and condenses. We get our rain here, and on this side we get our deserts. Okay. As the angle of insolation increases, the temperature increases. Solar noon occurs when the sun is highest in the sky. Celestial objects rise in the east and they set in the west. The zenith is a spot directly overhead, and constellations are groups that are near each other. The rotation is the spin of the earth, and that defines the day for us. Okay? The cause of night and day, I guess they gave it to you twice. 360 degrees in 24 hours equals 15 degrees per hour. And the evidence is the Foucault pendulum and the Coriolis effect. Revolution is the orbit. It defines the year. 360 degrees in 365 days gives us about 1 degree per day. The evidence we have for the revolution is the seasons, which is really caused by the tilt of the earth. Whoops, let me move that. And different constellations. All right, this chart is a chart that you got to get down. The direct rays of the sun over here during this days are over the equator for the equinoxes. And then December 21st, it's at 23.5 degrees south and then 23.5 degrees north. This is Capricorn, and this is Cancer. Okay. Altitude of the noon sun, 48. Hour longitude is 42. It kind of adds up to 90 if you notice that. Okay, duration of insolation, 12 hours for the equinoxes. Winter, 9. Summer, 15. Temperature, mild. Winter, cold, and hot. Okay. Is the sun ever 90 degrees over in New York State? No. It's only between 23.5 degrees south and 23.5 degrees north. Okay? If the Earth was tilted, would there be seasons? No. In fact, if the Earth was more tilted, the seasons would be even more exaggerated. Geocentric model, Earth-centered. The planets were moving around, but they were moving around because the Earth was spinning. Heliocentric is the sun-centered model. Okay, if a satellite is close to a star, orbital velocity is fast. The closer you are, and the more massive the star is, mass and distance affect gravity. Eccentricity is how uncircular it is, and we just did a whole bunch of stuff, so I'm going to leave that alone. Moon, one revolution for the moon, one time around, 27.3, full moon to full moon or new moon, 29.5. And you should memorize your moon chart. Here's the information about solar eclipses that we took a look at. Study them, lunar eclipses, the tides. We talked about spring tides versus neap tides. Let's look at solar system. First 4 planets are rocky. The others are gaseous. Okay, we learned about asteroids, meteorites, comets, the sun. Please read through this, the age of our solar system. Galaxies about 10 billion years old. And we'll go to the last pages here. Okay, our galaxy, like it says here, is 10 billion years old. Levels of organization. Start off with the youngest, for smallest, youngest. Let me go to the oldest. The oldest is the universe. The universe itself is the oldest. Then from the universe formed galaxies. The galaxies were made up of stars, so you needed stars before that. Okay. Of course, then we also have, from that, solar systems. And then from there we have planets and moons. All right, so I want to squeeze those in there too. The Big Bang Theory is that the theory that the universe started. And what is proof of the Big Bang? We talked about the red shift, that all the galaxies appear to be shifted to the red, and also that telescope discovered by accident the background cosmic radiation. Age of the universe, 10 to 15 billion years old, and the light years the distance from the sun. Now there's one thing that I didn't really cover very much, and that is learning about stars. So I put together some worksheets for you to do on stars. Thank you very much. Have a good summer. Good luck on your Regents exams. Had a great time teaching you. Keep in touch. Bye-bye.